Are you a data scientist? Do your tools make it easy to track your experiments, deploy to a machine learning model to production, and manage a GPU cluster? This free book from O'Reilly can teach you how to do all that. It's about tuning neural nets, making them scale, and then deploying them to the real world.
Can we actually predict stock prices with machine learning? Investors make educated guesses by analyzing data. They'll read the news, study the company history, industry trends. There are lots of data points that go into making a prediction. The prevailing theory is that stock prices are totally random and unpredictable. A blindfolded monkey throwing darts at a newspaper's financial pages could select a portfolio that would do just as well as one carefully selected by experts. But that raises the question, why do top firms like Morgan Stanley and Citigroup hire quantitative analysts to build predictive models? We have this idea of a trading floor being filled with adrenaline-infused men with loose ties running around yelling something into a phone, but these days you're more likely to see rows of machine learning experts quietly sitting in front of computer screens. In fact, about 70% of all orders on Wall Street are now placed by software. We're now living in the age of the algorithm. Hello world, it's Siraj, and today we're going to build a deep learning model to predict stock prices. Records of prices for traded commodities go back thousands of years. Merchants along popular silk routes would keep records of traded goods to try and predict price trends so that they could benefit from them. In finance, the field of quantitative analysts is about 25 years old, and even now it's still not fully accepted, understood, or widely used. Just like Google+. It's the study of how certain variables correlate with stock price behavior. One of the first attempts at this was made in the 70s by two British statisticians named Box and Jenkins using mainframe computers. The only historical data they had access to were prices and volume. They called their model ARIMA, and at the time it was slow and expensive to run, but by the 80s, things started to get interesting. Spreadsheets were invented so that firms could model companies' financial performance, and automated data collection became a reality, and with improvements in computing power, models could analyze data much faster. It was a renaissance on Wall Street. People were excited about the possibilities. They started showing up at seminars and discussing their techniques.
You should see what's going on at the bigger firms. I mean, I know all the information.
But all this quickly died down once people realized that what works is actually a very valuable secret.
All right, get the fuck off my boat.
Since then, the most successful quants have gone underground. In the past few years, we've seen lots of academic papers published using neural nets to predict stock prices with varying degrees of success. But until recently, the ability to build these models has been restricted to academics who spend their days writing very complex code. Now, with libraries like TensorFlow, anyone can build powerful predictive models trained on massive data sets. So let's build our own model using Keras with a TensorFlow backend. For our training data, we'll be using the daily closing price of the S&P 500 from January 2000 to August 2016. This is a series of data points indexed in time order, or a time series. Our goal will be to predict the closing price for any given date after training. We can load our data using a custom load data function. It essentially just reads our CSV file into an array of values and normalizes them. Rather than feeding those values directly into our model, normalizing them improves convergence. We'll use this equation to normalize each value to reflect percentage changes from the starting point. So we'll divide each price by the initial price and subtract 1. When our model later makes a prediction, we'll denormalize the data using this formula to get a real-world number out of it. To build our model, we'll first initialize it as sequential, since it will be a linear stack of layers. Then we'll add our first layer, which is an LSTM layer. So what is this? Let's back up for a bit. Recognize this beat? Sing the lyrics with me.
You don't have to say what you did, I already know, I found out from him.
It's easy to recall the words forward, but could we sing them backwards? No. The reason for this is because we learned these words in a sequence. It's conditional memory. We can access a word if we access the words before it. Memory matters when we have sequences. Our thoughts have persistence. But feed-forward neural nets don't. They accept a fixed size vector as input, like an image. So we couldn't use it to say predict the next frame in a movie because that would require a sequence of image vectors as inputs, not just one, since the probability of a certain event happening would depend on what happened every every frame before it. We need a way to allow information to persist, and that's why we'll use a recurrent neural net. Recurrent nets can accept sequences of vectors as inputs. So recall that for feed-forward neural nets, the hidden layer's weights are based only on the input data. But in a recurrent net, the hidden layer is a combination of the input data at the current time step and the hidden layer at a previous time step. The hidden layer is constantly changing as it gets more inputs, and the only way to reach these hidden states is with the correct sequence of inputs. This is how memory is incorporated in, and we can model this process mathematically. So this hidden state at a given time step is a function of the input at that same time step modified by a weight matrix, like the ones used in feed-forward nets, added to the hidden state of the previous time step multiplied by its own hidden state to hidden state matrix, otherwise known as a transition matrix. And because this feedback loop is occurring at every time step in the series, each hidden state has traces of not only the previous hidden state, but also of all of those that preceded it. That's why we call it recurrent. In a way, we can think of it as copies of the same network, each passing a message to the next. So that's the great thing about recurrent nets. They're able to connect previous data with the present task, but we still have a problem. Take a look at this paragraph. It starts off with, "I hope senpai will notice me," and ends with, "She is my friend, he is my senpai." Let's say we wanted to train a model to predict this last word given all the other words. We need the context from the very beginning of the sequence to know that this word is probably senpai, not something like buddy or mate. In a regular recurrent nets, memories become more subtle as they fade into the past, since the error signal from later time steps doesn't make it far enough back in time to influence the network at earlier time steps during backpropagation. Yoshua Bengio called this the vanishing gradient problem in one of his most frequently cited papers titled "Learning Long-Term Dependencies with Gradient Descent is Difficult." Love the bluntness. A popular solution to this is a modification to recurrent nets called long short-term memory. Normally, neurons are units that apply an activation function, like a sigmoid, to a linear combination of their inputs. In an LSTM recurrent net, we instead replace these neurons with what are called memory cells. Each cell has an input gate, an output gate, and an internal state that feeds into itself across time steps with a constant weight of 1. This eliminates the vanishing gradient problem, since any gradient that flows into this self-recurrent unit during backprop is preserved indefinitely, since errors multiplied by 1 still have the same value. Each gate is an activation function like sigmoid. During the forward pass, the input gate learns when to let activation pass into the cell, and the output gate learns when to let activation pass out of it. During the backward pass, the output gate learns when to let error flow into the cell, and the input gate learns when to let it flow out of the cell through the rest of the network. So despite everything else in a recurrent net staying the same, doing this more powerful update equation for our hidden state results in our network being able to remember long-term dependencies. So for our LSTM layer, we'll set our input dimension to 1 and say we want 50 units in this layer. Setting return sequences to true means this layer's output is always fed into the next layer. All its activations can be seen as the sequence of predictions this first layer has made from the input sequence. We'll add 20% dropout to this layer, then initialize our second layer as another LSTM with 100 units, and set return sequence to false on it, since its output is only fed to the next layer at the end of the sequence. It doesn't output a prediction for the sequence, instead a prediction vector for the whole input sequence. We'll use the linear dense layer to aggregate the data from this prediction vector into one single value. Then we can compile our model using a popular loss function called mean squared error, and use gradient descent as our optimizer, labeled RMS prop. We'll train our model with the fit function, then we can test it to see what it predicts for the next 50 steps at several points in our graph, and visualize it using Matplotlib. It seems that for a lot of the price movements, especially the big ones, there is quite the correlation between our model's prediction and the actual data. So time to make some money and play some TI. But will our model be able to correctly predict the closing price 100% of the time? Hell to the no. It's an analytical tool to help us make educated guesses about the direction of the market that is slightly better than random. So to break it down, recurrent nets can model sequential data, since at each time step, the hidden state is affected by the input and the previous hidden state. A solution to the vanishing gradient problem for recurrent nets is to use long short-term memory cells to remember long-term dependencies. And we can use use LSTM networks to make predictions for time series data easily using Keras and TensorFlow. The winner of the coding challenge from the last video is Vishal Bachu. Vishal used transfer learning to create a classifier for cats and dogs. He chose a layer from a pre-trained TensorFlow model and built his own custom convolutional net on top of it to make training much faster. Wizard of the Week. And the runner-up is Jie Shun Si. I loved how he added a command line interface for users to input their images. The coding challenge for this video is to use 3 different inputs instead of just one to train your LSTM network to predict the price of Google stock. Details are in the README. Post your GitHub link in the comments and I'll announce the winner in a week. Please subscribe for more videos like this, and for now, I gotta count my stacks of layers, so thanks for watching.